we have solved a long-standing open question. This presentation is about new insights into isotopic activity ratios of discharges from nuclear facilities. Discrepancies are observed between what we expect to see and what we do see. So the observations from medical isotope extraction facilities are always found on the left side of the separation line, whereas simulations by Paul See, by Esslinger, and by others predict that the isotopic ratios from isotopic production is found on the nuclear explosion domain. But this is not the case. So why? We are studying this issue with data from medical isotope production facilities, and here you see the distribution of STUX measurements at two medical isotope production facilities. And these STUX data were measured by a large team of PNNL and ISTI and others, and the operators, of course. And you see here the list of authors to this presentation on the top. So this slide gives you an overview of the hypothetical explanations that were checked in this work. I don't read them out because we go through them one by one with one slide for each of the hypothetical explanations. Let's start with simulation methods for understanding the ratios of discharge time. So this is the method. It starts with initiation of the radioxenon inventory of the targets before dissolution of the targets, and also inferring the radioiodine inventory of the targets. Then we do radioactive decay and ingrowth in the time of after irradiation ends and before the targets are dissolved. Then we do further ingrowth and decay of the inventory that is contained somewhere in the abatement system of the facility. And also we do incremental accumulation of inventory in the abatement system. Now we go through the hypothesis by hypothesis, and this is the first one. The brown dashed line shows simply radioactive decay of a pure iodine holdup, better to say of the radioxenon coming out of this pure iodine holdup. The line is found on the left side of the separation line, so that's the right direction, but it's not going far enough to explain all the observations. The second hypothesis, now shown in dark magenta, is the accumulation of xenon from iodine from successive target dissolutions. So for every day we add some more iodine and see how it develops if this accumulates. The curve is found on the left side of the separation line, but it goes a little further, but it's still too low and not going far enough. Next hypothesis is shown in brown dots on a bending curve. It's the accumulation of pure iodine from successive target dissolutions. On the left side of the separation line, this is found basically on the left side of the separation line. It goes a bit further, but it's still not going far enough to explain all observations. And this hypothesis is shown in blue dots, and they are connected with dotted lines, but be careful, it's not indicating a trajectory that develops over time for the same air mass. So every dot here is a different simulation, and it's always a one-time mixing of decayed radioxenon gases with a fresh contribution of a fresh release from just dissolved targets. And the dotted lines are just to guide the eyes how these are connected. There are three such lines, and one is for a dilution ratio of 1 to 10, and another one is 1 to 1,000, and the third one is 1 to 100,000. And what you can see is that these lines are filling the whole space. Here another version of mixing, and you see blue dots again, but now they are for one-time mixing of the decay products from a stock of pure radioiodine mixed with fresh radioxenon from dissolving a irradiated target. And again, it fills the whole space, but it goes even further. It bends even further away from the separation line. And these two different ways of mixing are actually seen at two different medical isotope production facilities. And here you see on the 4-isotope plot comparison of the key simulations with time series of MIP, medical isotope production facility discharge rates. The colorful trajectory is for decay of discharges during the outage period. And there's evidence that mixing is the only process that can explain the data. So all the other processes that are also indicated here cannot reach to the full distribution of the medical isotope production facility data at the stack, so where they leave the facility and then of course they go through the atmosphere and further change, but the emissions from the medical isotope production facility are all found on the left side of the separation line. This shows now for other multi-isotope plots. These are the 3-isotope ratio plots, and again, it's a demonstration of what effect the 4 hypothetical explanations have on the 4 different combinations of 3 isotopes. And again, it's clear that the mixing is the only physical process that can explain the full data spread, except for a ratio combination not including xenon-135. That's the one on the top left corner. I want to have a little excursion here and also explain the effect caused by using non-representative values to substitute for a measurement below MDR. So I did a little experiment. I used hypothetical data for a full year to be used to generate annual total discharges for each isotope. And this is shown for 2 different isotopes in each of the top plots. And the bottom plot shows the results of 3 different ways to substitute non-detections with is estimating when accumulating annual total discharges from these daily values. In case one of the 2 isotopes was not above the minimum detectable rate, this applies only to the 2 isotopes shown in blue on top, and there is a line drawn below the red dots. The red dots are all above the minimum detectable rate, and the blue dots are mostly below, but a few are above. How are those concentrations that are not observed substituted? And the first method is do not do a substitution at all. This means just drop this contribution from this isotope at this day, on this day. The second is use the minimum detectable rate. And the third method is use 0. And in the 4-isotope plot shown on the bottom, the ratio of annual total discharges show large discrepancies. Despite they use all the same hypothetical data as an input, the real value is anywhere between 0 and MDR, but it's substituted in different ways. And this causes a huge uncertainty by several orders of magnitude. So the green markers are indicating where the annual total would be reported, and the black star is indicating where the real annual isotopic ratios are, the accumulation with known data, because of course I fabricated the data so I know them. So there is only one way of using substituting the data that creates results very close to the real value, and this is replacing by the MDR. Everything else is causing big troubles, big differences, and you don't get the realistic data. So that is a problem that you may see with using annual total reports. I'm already coming to the summary and conclusion of this presentation. Several hypotheses are tested to explain the shift of the 2 metastable isotopic ratios towards the lower values, so and to cross the screening line for medical isotope production facilities. The decay products from pure radioiodine accumulation of xenon and iodine from successive targeted solutions can explain a little shift, but not enough. And the full spread of the shift and the activity ratios observed with STAX data can only be explained by one-time mixing of decayed gases with a fresh radioxenon release. And this was an open question actually for, I think, 15 years, and the strongest mechanism that can explain that I showed that can explain this shift was already published in 2006, but it was just one out of several hypotheses, and now I walked them through one by one, and I think that the answer is now clear. What is the main reason for this shift across the separation line? Now, any questions left to be answered? The floor is open. Thank you very much for your attention.